Yeah, hello everybody. My name is Lars Kunze. I'm a research fellow at the University of Birmingham, and this is joint work with Michael Beetz. We are looking at the problem of reasoning about everyday manipulation action in the context of personal and service robotics. So let me start by motivating the challenges. So today we have millions of robots that operate in factories worldwide. They perform their tasks very efficiently and very effectively. So they can only do this because they are... Yeah. Okay. So they can only do this because they're mainly pre-programmed for one task, and for one task only. They do this very repetitively, so at very high speed and with very high precision. However, this is very different compared to personal robot assistants who operate in human environments. They have to deal with a high amount of dynamics in their environment. And this is because people are around and they move objects around and they perform activities. So these robots will never encounter the same situation twice. So they have to deal with incompleteness of incomplete information. They have to perform their task under varying conditions. And so therefore we need really flexible and robust ways to establish such behaviors. And we need ways to program these robots. Also in with respect to an open-ended set of tasks, because at the time of programming, we don't know what these robots will do eventually. And our answer to this is we should equip these robots with naive physics and common sense reasoning capabilities so that they embedded in their control programs so that they can solve these problems as good as humans can. So I would like to show you a video of two of our robots in our lab. So this is in context of the RoboHow project. And these robots make pancakes. So they have to do lots of decisions here. They have to reason about which robot is capable of what actions. They have to reason about where to find objects in the environment. For example, here the pancake mix, right? So this is all common sense knowledge. But in this work, we are mainly interested in the manipulation actions. So the robot brings this pancake mix now to the counter, to another robot. And this robot is mainly performing two actions. So one is pouring the pancake mix onto the pancake maker, and then using the spatula, the robot is flipping the pancake, right? And we really have to reason about this in all kinds of details in order to accomplish this task. Almost. Okay, so what we really would like to have is some kind of consequence-based way to describe these actions. So here's some Lisp pseudocode to perform or describe a pouring action. We have an object that is a pancake mix, and this is in the mug. And then the target location is the pancake maker. And what we would like to do is we want to describe the desired and the undesired effects, so that we want to have a small round pancake in the center of the pancake maker, but we don't want to spill anything. So we don't want to specify the explicit angles and parameters for the control programs, but the robot should come up with these via reasoning mechanisms. So if we look at approaches in classical AI, there has been lots of work in naive physics reasoning, representations, and mainly this work is based on logical axiomatizations. So they start with the real-world situation and a goal that they're trying to prove. So they abstract this and formalize this as a logical problem. They have some kind of action script, and they use, for example, the event calculus then to prove that after performing these actions, the pancake mix is on the pancake maker. However, we think in robotics there are several problems with this approach. So for one, this level of abstraction is not detailed enough because it abstracts away, for example, the poses or the positions and the orientation of the hands, and this is really critical, as you saw, for really pouring the pancake mix into the center. Secondly, it's really hard to deal with non-deterministic and concurrent action in logic. So imagine a robot driving through an environment, and at the same time it's turning its camera on its head. So you have to describe in logic what the robot will see. So this becomes very complicated. And also, we want to reason about variants of the problems. As I'm motivated, so the robot has to deal with different conditions. So in one case, the pancake mix is maybe in a bottle and in the next day it's in a mug or so. This should also be robust to some variations. So what we are proposing is extending this approach. So we start also with a logical axiomatization here. And this is connected also to a knowledge base. In this knowledge base, we have information about the robot's environment. So it's connected to a semantic map and also to physical models. We can then use these physical models to instantiate a physics-based simulation and run and execute this robot control program or the plan of the robot in the simulator. What we are doing is we're monitoring the world state, so the state evolution of the simulation, and also we monitor the actions of the robot. So we log all these information. So this is all sub-symbolic here at this level. And then we translate these back into timelines. So these are basically descriptions what has happened over time, and then we can reason about effects of the actions over time. So let me again show you a video how this works. So this envisioning framework that we've developed uses Prolog as an interface. So you can, from Prolog, you can start up this simulation, and Prolog is also connected to our knowledge base, so which is basically an ontology and a semantic map. So we can load the environment model and also the robot from Prolog, and then we can start this reasoning process in Prolog by selecting several of the actions of the robot and then performing the task. So this work also required us to extend the rigid body simulation, which is here gazebo. I don't know whether you see the red particles here. So we approximated the liquid with a particle model, and they also have some kind of to simulate the viscosity. So we manipulated the friction and so on. And here you see now different effects if we use different parameterizations. Then we apply kind of a magic cooking routine, which clusters these particles to a deformable pancake model, and then the robot can flip it. So all this is embedded in this Prolog backtracking mechanism. So every tree in the every branch in the tree of the proof tree is basically a different configuration of the robot's actions. And you can, of course, also in the simulation introduce noise and error models here to make it more robust. So here again you see now different angles that are used in order to push the spatula under the pancake. And it's also important to reason about what does it actually mean to push the spatula under the pancake. It actually means only to have the blade of the pancake of the spatula under the pancake. And again, so this is very difficult to describe such behaviors in logic so that you push from the oven. Okay. So, but embedded in Prolog now, we have all these locked traces, and then we can formulate queries. So we can ask whether the pancake mix was built onto the counter, and then we get the answers back in which time intervals this happened and in which experiments. So it's basically a virtual knowledge base that we have with rich experience of the robot. So, and if we visualize these timelines, it looks maybe similar to this. So in yellow at the top here, you see the actions of the robot. So the pouring, flipping, and placing of the pancake. And then there are sub-actions here again. So you have a hierarchical description of the action model of the robot. And here below you see more kind of fluents that hold at certain points in time or over time intervals. And these are then directly generated from the log data. So they are automatically extracted, and Prolog can these now do queries and reasoning with this. So just to repeat, this kind of the basic idea is we have a logical description and an action plan, which is fully instantiated. We run our simulation here, and then we come up with one timeline, and we can do this with different parameterization to get loads of data. So this is kind of a little bit more the architecture of the system. Here we use NoRob that was developed in our lab, and which is based on the web ontology language. So it's a ontological representation, or it's based in description logic. And This is all linked to physics-based models, so we can instantiate the robot control, the physics-based simulator, Gazebo here, which is a rigid body simulation. We extended this with several new behaviors like mixing liquids, for example, or also structures that break. And the robot control can be an arbitrary control program. So the whole framework is implemented in ROS. So you can put any robot control program there as long as it provides certain interfaces that we can monitor here the actions of the program. So then this gets back translated automatically. And you can actually also already put some interesting queries in your first query when you're running the whole pipeline. Okay, so some more details. I mean, there are lots more details in the paper, but so what information we are accessing from the simulation is basically position, orientation, velocities, bounding boxes of the objects, and contacts between objects, including their forces. And then we have a predicate defined, which allows us to access all this information from the simulator. So here an example is the position of an object and a specific point in time, but this can also be an interval, and then you get the whole trace back. And if you know Prolog, so you can also leave these variables open, and then it will find the right objects and intervals for you. So having such a grounding interface here for accessing the log traces from the simulation, we're able to also define high-level kind of predicates, like one object is above each another, exactly when the bounding box of the first object is above the second bounding box. So these can be defined using heuristics, but these predicates can also be learned, as we have shown in some examples. And there are several of these directional or proximity relations that we've defined or learned. Maybe one short word also on liquids. So because these are a little bit more tricky to handle in the simulation, because we don't want to talk about the liquid as a whole, but we also don't want to address this at a particle level, right? So what we are doing is some geometric clustering, and so then we can reason about the predicates and fluents that hold for all these clusters. So if you look at this kind of more visually, so we start off with one cluster of pancake mix in the mug, and then during the pouring action there are lots of intermediate clusters are generated, but whenever there's some qualitative change within these clusters, so we instantiate new clusters, and this will stabilize at some point. Okay, so this gives us a really nice tool to generate a really big virtual knowledge base. From the knowledge base, we get the parameter space of these actions, and we have also shown in other work how these parameter spaces can be initialized through human demonstration, where humans used an interface to guide, kind of give initial guesses what might be the right parameter for the robot. So then we pick one of these parameters here, and then we run this envisioning process, and as I said, so these will correspond to different traces in the tree. So what can we do with this? So as one example, we can learn some action models with this, and we are doing hundreds of these simulations in order to learn maybe a model for this or to reason about this, where we also varied, for example, the context with few or less lower amount of particles in a container or different types of containers, and this leads all to qualitative different outcomes. And then the robot can also decide which action parameters are required in order to produce a certain size of pancake, so small pancake, medium, or large pancake, for example. Okay, so this brings me to the end of the talk. So the main contribution of this work is this envisioning framework, which allows to reason about robot manipulation actions at a very adequate level. So we have also provided a physics-based library that can be used kind of to look at similar problems, like if the robot's not making pancakes, for example, but an omelette, so it can reuse these physics models, and we argue that this is a better way to scale these behaviors in comparison in order to kind of when you want to extend a logical theory. And this can be important. I think it can be a nice bridge, but because on one side we have very detailed manipulation actions, and the outcome of these are these qualitative timelines, which can then be used for monitoring or planning purposes for diagnosing these tasks. So with this, I will end, and if you have any questions, happy to answer them.
Thank you.